Kirchhoff's voltage law, or KVL, is a fundamental law when it comes to analyzing circuits. It says that the directed, or algebraic, sum of the potential differences around any closed loop is equal to zero. Algebraic in this context means that we need to account for signs, or polarities, of circuit elements in the sum. In simpler terms, the combined magnitude of voltage rises across the loop must be equal to its drops. When accounting for polarities, we assign what we know first and then make a guess for the polarities of undefined voltage changes. For example, in this circuit, we'll take the right loop first. The 3-volt battery's polarity is already shown. Since the resistor is the only other component in this loop, and we know by KVL that the rises must equal the drops, we can guess that its polarity is going to oppose the battery's. If we take the loop to be clockwise, the battery's polarity goes from negative to positive, or a rise, and the resistor's to be positive to negative, or a drop, as is consistent with resistors. The equation can now be written. 3 volts, the battery's increase, plus negative V2, the resistor's decrease, is equal to 0. Rearranging gives V2 equals 3 volts. We can verify this by the fact that the resistor and battery are in parallel, and voltage drops equally across parallel branches. As we know the potential to drop 3 volts across the battery between these two nodes, the potential across the resistor must also drop 3 volts. If we put the assumed polarities for the resistor the other way, going from negative to positive in a loop, its sign in the equation would instead be positive, and rearranging it for V2 would give minus 3 volts. This is the same magnitude, but opposite direction of our previous answer, meaning that if we get a negative voltage, we must have the polarity switched around. We can still use this answer in further examination as long as we flip the polarity in the diagram and use the positive value. Let's go to the left loop. We'll assume the polarity of V1 to be positive to negative in the clockwise as voltage drops across resistors. Using the values and polarities we've established, the equation is 5 volts minus the value of V1 plus 3 volts equals 0, and rearranging is V1 equals 5 volts plus 3 volts, or 8 volts. We have now found all voltages in the circuit. Kirchhoff's voltage law is used in many questions encountered in circuit analysis and is especially important when making use of nodal analysis. Remember to always verify your solutions when possible and pay attention to polarities and signs when using this law.